Recall the idea of a coordinate system for a vector space V. We have generators, A1 through AN, say, of the vector space V, so that every vector in V can be written as a linear combination of the generators. And we represent a vector V by its coordinate representation, that is, the vector formed by the coefficients in this linear combination. And we raise the question, how can we ensure that every vector has just one coordinate representation? The answer is to ensure that these generators form a basis. So we'll prove the unique representation lemma, which says that if A1 through AM are a basis for a vector space V, then for any vector little v in that vector space, there's exactly one representation of that vector in terms of those basis vectors. So here's the proof. Let V be any vector in the vector space. Now, the vectors A1 through AN span the vector space, so there's at least one way of representing V as a linear combination. Suppose there are two such representations with the coefficients alpha 1 through alpha n and the coefficients beta 1 through beta n. Now, by subtracting one from the other, we get the zero vector. And now by collecting coefficients corresponding to the same vectors, we get 0 as this linear combination. Now, because those vectors are linearly independent, it follows that the coefficients must all be 0. It must be a trivial linear combination. So alpha 1 minus beta 1 equals 0, and so on. And that shows that alpha 1 equals beta 1, and so on. So the two representations are actually just one. A basis in a graph is a spanning forest, and the unique representation lemma shows us that for each edge, x, y, in the graph, there is a path from x to y in the spanning forest, and there's only one such path.